everyone, welcome back. This is the second part of the 19th lecture in the series Mathematical Methods for Economics. And in the first part, I introduced to you the concept of an asymptote, and also we talked about what a vertical asymptote is, when it exists, and I gave you this problem. So if you look at what you have on the slide here, I asked you to find the vertical asymptote or asymptotes if the asymptote exists. So here the function is x squared minus 25 divided by x minus 5. Now, typically students have this first response because when you look at the denominator, you can see that the denominator is 0 when x is equal to 5. So you have to ask yourself if this qualifies, if x equal to 5 qualifies as a vertical asymptote. And please, so this is where students generally go wrong, because here you have to understand that it's not just about the 0 for denominator. So if x is approaching 5, you have to make sure that the function tends to infinity or minus infinity as per the definition. Now in this case, if you notice, if we put x equal to 5 in both the numerator and the denominator, the function actually is undefined. So let me show you the visual here. At 5, the function is undefined, right? In fact, if we think in terms of the limit of the function as x tends to 5 is actually 10. And if you're wondering about this, in case you're wondering about this, I have talked about this example in my first lecture on limits, so you can go back to it and revise it and come back to this problem again. So the point here is that the function does not tend to infinity or minus infinity as x tends to 5. So x equal to 5 does not qualify as a vertical asymptote. Okay, so in fact this particular function, you can see visually here also that this particular function does not have a vertical asymptote. This is another example that I have to make you check for vertical asymptotes. So here you can see here that x equal to 1, x equal to minus 1 will both qualify as vertical asymptotes, because you can see the function is in this case, to the right of 1, the function is shooting off to infinity. To the left of 1, it's shooting off to minus infinity. And similarly, you can see the behavior on both sides of x equal to minus 1 as well. But yes, the limits don't exist, so these are very much vertical asymptotes. And let me move back one slide. So the question that can emerge here is that can the graph of a function cross a vertical asymptote? And here, please remember that for a rational function, vertical asymptote is like the sacred brick wall that you cannot cross. Why is that? Because the vertical asymptote corresponds to the zeros of the denominator, right? And if that is the case, the function, if it is a vertical asymptote, then the function is tending to infinity or minus infinity, and as x is approaching the vertical asymptote, so you can't possibly have an intersection for a rational function between a graph and the vertical asymptote. Okay. Then one can also ask the question, how many vertical asymptotes can you have? So in this particular picture, you have 2 vertical asymptotes. Can you have more? And yes, you can have infinitely large number of vertical asymptotes here. So look at this graph here. And again, depending on how many zeros you have in the denominator, you can have as many vertical asymptotes. You can have infinitely large number of vertical asymptotes. Let's now talk about what a horizontal asymptote is. So horizontal asymptote, because it's a horizontal line, it's specified by the y coordinate. And basically here we are talking of y equal to L as a horizontal asymptote if the function as x tends to infinity or as x tends to minus infinity, if the function tends to this limit capital L. Okay, so basically here, what if you notice here, we are in this case for a horizontal asymptote, we are talking about the end behavior of a function, right? We're talking about what happens to the function as x tends to infinity or as x tends to minus infinity. Now, at this point, let us just stop for a few moments. I don't want to go extremely fast and not have you absorb the concept. What is the difference in the conceptual understanding between a vertical asymptote and a horizontal asymptote. See, what happens for a vertical asymptote is that the function shoots off to infinity or minus infinity, right? It is the function or y that shoots off to infinity or minus infinity as x tends to a particular number a. So that gives you the vertical asymptote. What happens in a horizontal asymptote is that you are getting x, okay, not y. It's x that is tending to infinity. So basically here you're taking the limit at infinity, and the result that you get for the limit, which is L here, if it exists, then that is our horizontal asymptote. Let's take a look at a few examples to understand this. And now what I'm going to do is, for the examples that we do for horizontal asymptotes, I would like you to look at horizontal asymptotes and vertical asymptotes together. Okay, so check for both if any one of them or both exist. Okay, first of all, let's get the horizontal asymptote aspect out of the picture, out of the way here. So what we have here is a curve, and you can see that as x tends to infinity, the function tends to capital A. And as x tends to minus infinity, the function tends to capital B. Here in this case, so do you see here we are taking the limits at infinity. When I ask you to calculate a horizontal asymptote, you are going to see how the function will behave as x tends to infinity or minus infinity. So in this case, both these lines, y equal to a and y equal to b, these qualify as horizontal asymptotes. Okay? These tell you about the end behavior of a function. Let's look at this particular example. In this example, the function is x squared plus 12 divided by x squared plus 5. Now, in this case, first of all, suppose I ask you, does this function have a vertical asymptote? The answer clearly is no, because you don't see the denominator going off to 0 anywhere. So, the vertical asymptote here does not exist. Now, what about the horizontal asymptote? To calculate the horizontal asymptote, I'm going to look at how the function behaves as x tends to infinity or minus infinity. So, let's look at that. The limit of the function f of x as x tends to infinity is what? Now, all of you are familiar with calculating limits at infinity, right? How do you do that? You take the highest power of the term in the denominator. So, you take x squared common, right, in both the numerator and the denominator, which will then give you x squared times 1 plus 12 by x squared in the numerator. And in the denominator, if I take x squared common, I take the highest power of x common in the denominator and the numerator as well. So, x squared times 1 plus 5 by x squared. So, now I can apply my limit as you can see here, that as x tends to infinity, 12 by x squared. So, here x squared and x squared get cancelled, and as x tends to infinity, 12 by x squared will tend to 0, 5 by x squared will tend to 0, and the limit here is 1. So, here y equal to 1 is your horizontal asymptote, and you can see here that even as x tends to minus infinity, the function is tending to 1. So, y equal to 1 is your horizontal asymptote. This is the case for this particular function. Now, what I'm going to do is, I'm not going to be using these same detailed procedures every time. There's a quick way of calculating limits at infinity if you have gone through my first lecture on limits. What we do is, we look for the dominant terms in both the numerator and the denominator for a rational function. And you can see here that the dominant term here is x squared. And even in the denominator, the dominant term is x squared. So, basically the function, as x becomes larger and larger, the function behaves like x squared divided by x squared, which is nothing but 1. So, that is how we typically go about calculating limits at infinity. And the same procedure will work even for x tending to minus infinity, because as x becomes larger and larger in the negative direction, the function it's these two terms that will dominate, x squared in the numerator and x squared in the denominator. So, basically the function approaches 1. And let's take a visual look. Let's take a look at the visual here. So here you can see there is no vertical asymptote. This curve is approaching y equal to 1 asymptotically in both directions. So as x tends to infinity and as well as x tends to minus infinity, the curve is approaching this horizontal asymptote arbitrarily closely. A related question that people ask is, can we have any intersection between the graph of the function here and the horizontal asymptote? So if we were to actually calculate things, for particular functions, so the procedure here would be, because our horizontal asymptote here is y equal to 1. So what we're going to do is, because this corresponds to a function here, so our function is y is equal to x squared plus 12 divided by x squared plus 5. So the question basically boils down to asking, is x squared plus 12 divided by x squared plus 5 equal to 1 for any value of x? Now clearly you can see that this is not going to be happening for any value of x, because when you put x squared plus 12 equal to x squared plus 5, the x squared terms will get cancelled on both sides, and clearly 12 can't be equal to 5. So there is no intersection here between the function and the horizontal asymptote, and this is exactly what our graph is also showing, right? Let us look at the next example now. Again, I would ask you to check for both horizontal and vertical asymptotes. Typically in the exam you're asked to test the function and find all the asymptotes of the function whichever exist. But because we haven't done oblique asymptote right now, so far you are in a position to calculate both the horizontal and the vertical asymptotes. So in this case, a function is given by x minus 1 divided by x squared plus 2x minus 15. Now, x minus 1 divided by x squared plus 2x minus 15, actually, so if I want to find the vertical asymptote, a clever way of doing it is to write the denominator. Let's factorize it. So that then gives us x minus 3 times x plus 5. If I want to see what the vertical asymptotes here are, there are two here. One would be x equal to 3 and the second would be x equal to minus 5. So here there is no problem in terms of there being a common factor or anything. So we can take these as the vertical asymptotes. If I want to find what the horizontal asymptote is, I have to take the limit at infinity. And here again, let's look for the terms that dominate in both the numerator and the denominator. Now, in the numerator, the term that dominates is x, and in the denominator, the term that dominates is x squared. So basically, as x becomes larger and larger, the function is going to behave like the fraction x divided by x squared, which is nothing but 1 by x. So you can either do the limit calculation the way you always do, or you can just look for these dominating terms and see how the function will behave. So the function behaves like 1 by x, right? And because a function behaves like 1 by x, so as x tends to infinity or minus infinity, what will happen to the function? The function will tend to 0. And that is why a horizontal asymptote you can see here is y equal to 0. So this is the picture of the function that we were just discussing. You have the x-axis, which is y equal to 0 as the horizontal asymptote, and you have two vertical asymptotes here, which are minus 5 and 3, and you can see that all these asymptotes, they fall beautifully in line with the basic points that I've been making since the very beginning. One is in terms of the distance between the graph of the function and the asymptote. The other is in terms of, you can see here the function is, for a vertical asymptote, the function is tending to infinity or minus infinity as x tends to minus 5 from the left or from the right. The limit does not exist. Here you can see that there is a point of intersection also with between the graph and the horizontal asymptote, and actually let's see. So if you go back, you can see what will be the point of intersection, because y is equal to 0. I think it's very obvious what the point of intersection would be. This would be at x equal to 1, and you can see that yes, the line also qualifies as a horizontal asymptote, even though there is a point of intersection, because here we're basically talking of behavior, the end behavior for a horizontal asymptote. We're talking of the end behavior of a function as x tends to infinity or minus infinity. So x equal to 1 is not coming into, not conflicting with that. Right, this is example 9 now, and in this example our function is h of x, which is given by x squared divided by 4x squared plus 3x minus 1, which again here you can factorize the denominator to get x squared divided by 4x minus 1 times x plus 1, so that the vertical asymptotes are x equal to 1 by 4 and x equal to minus 1. To get your horizontal asymptote, you're going to be taking the limits at infinity, and you'll see that as x tends to infinity or minus infinity, because here you can see the denominator and the numerator are the highest, the leading term is x squared in the numerator and 4x squared in the denominator, and you can see that the degree of the numerator is the same as the degree of the denominator. So basically the function will tend to the limit 1 by 4 as x tends to infinity or minus infinity, right? So the horizontal asymptote is 1 by 4, and this probably you can try drawing on your own, or use a graphing utility like Desmos or GeoGebra. Try and get a visual sense of things wherever possible. Okay, so let me do one more example for horizontal and vertical asymptotes, so that you warm up to these two kinds of asymptotes at least for a start, and then we'll see how we will introduce at least the concept of an oblique asymptote. Okay, in this case a function is given by 3x minus 2 divided by square root of 4x squared plus 5. No vertical asymptote, because you can't have the denominator going off to 0 here, so no vertical asymptote. And if you look at the horizontal asymptote here, because there's a square root in the denominator, there's a little bit of a mathematical manipulation which is required, nothing difficult, but you can see here that if I take x squared common in the denominator, x squared, if I take that as common, I'll get in brackets 4 plus 5 by x squared, right, in the denominator, and the whole thing will be under the square root sign. Now remember from one of the earlier lectures, if you go back to my lecture on absolute value, I told you that mod x is equal to square root of x squared by definition, right? Because mod x is always going to be something non-negative, so that's by definition equal to square root of x squared. Now once I take this out of the square root sign, so if I take the square root of x squared out of this square root out of the system, basically out of this 4 plus 5 by x squared product, so then outside I will get mod x, and that will be multiplied by square root of 4 plus 5 by x squared. And let's see how we can manipulate that. In the numerator, I've taken x common, because basically once you take x squared out of the square root sign, the highest power of x will be 1. So we always look at, take the highest power of x as in the denominator as common to calculate limits at infinity. So in this case, you have the limit of the function as x tends to infinity being expressed as x times 3 minus 2 by x divided by mod x times square root of 4 plus 5 by x squared. Now note here that because x is tending to infinity, basically we are talking about x, it is tending to a very large number, it is growing without bound, but it's still positive, right? Because it's heading to positive infinity. So that by definition, if you remember your definition of mod x is going to be nothing but x if x is greater than or equal to 0, and it is negative x if x is negative, right? So mod x, because x tends to positive infinity, mod x is going to be equal to x, right? And the numerator, in the numerator 2 by x will tend to 0, 5 by x squared will tend to 0. So basically your x and mod x will get cancelled here, and you'll be left with 3 divided by square root of 4, which is nothing but 3 by 2. So as x tends to infinity, the function tends to 3 by 2. However, if x tends to minus infinity, then the limit of the function is calculated in this fashion. The limit of the function as x tends to minus infinity will be given by applying the limit to this manipulation. But now mod x is going to be negative x, so that when x cancels with negative x, you're going to get a minus, right? And this part of your calculation will still contribute a 3 by 2. So the limit of the function as x tends to minus infinity is minus 3 by 2. And in this case, you have a situation where you have two horizontal asymptotes, y equal to 3 by 2 and y equal to minus 3 by 2. And let me quickly show you a picture of this, which I drew in the Desmos graphing utility. That sounded, that actually I use Mathematica and Desmos both. So this graph turned out neater in this particular graphing utility. So you can see that there are two horizontal asymptotes. As x tends to infinity, right, the function tends to 3 by 2. As x tends to minus infinity, the function tends to minus 3 by 2, okay? So this is your function where there are two horizontal asymptotes. In fact, I can ask you a related question. How many horizontal asymptotes can a rational function have? So when we talk of rational functions and limits at infinity, how many maximum number of horizontal asymptotes can we have? So actually we can talk of three cases here, and this will then give you this will initiate us into the discussion for the oblique asymptote, but let's just talk about the three cases quickly before we wind up for today. The first case is where the degree of the numerator for a rational function is equal to degree of denominator. So this is one of the functions that we did. The degree of the numerator is equal to 2, which is equal to the degree of the denominator. And basically when we take the limit at infinity or minus infinity, there the function behaves like, in this case, in this particular example, the function tends to 1 by 4. It doesn't matter whether x tends to infinity or minus infinity. Both these limits, the calculation will give you 1 by 4. So here you have only one horizontal asymptote. Similarly, if the degree of the numerator is less than the degree of the denominator, this is another example that we did just a little while ago. Here also we see that whether x tends to infinity or minus infinity, the function will behave like the fraction x by x squared, right? And this is nothing but 1 by x. But it doesn't matter whether x is tending to infinity or minus infinity, you get a unique value here, which is 0. So whichever case you took, we have basically considered these two cases for horizontal asymptotes. We got only one asymptote, one horizontal asymptote. Now the third possibility for a rational function is where the degree of the numerator is larger than the degree of the denominator. So for example, if I give you the function x squared minus 3 divided by 2x minus 4, you can see that the degree of the numerator here is 2 and the degree of the denominator here is 1, the highest degree. So this is a function where for large values of x, a function behaves like the fraction x squared divided by 2x, which is what? X by 2. Now this will actually turn your things all haywire, because if you take the limit of the function as x tends to infinity, you're going to get infinity. And if you take the limit of the function as x tends to minus infinity, because it's x here, so it's going to be guided by minus infinity now. So the limit is minus infinity as x tends to minus infinity. But note here that these are not finite limits. These limits don't exist. So when the degree of the numerator is greater than the degree of the denominator, you can't have a horizontal asymptote. In this case, we talk about having an oblique or a slant asymptote, in particular for the case where the degree of the numerator is 1 greater than the degree of the denominator. So in particular, if we have a function where a polynomial p of x is divided by q of x, and the degree of the polynomial p of x is 1 greater, remember we are talking of only 1 greater for our course than that of the polynomial q of x, then we say the function will have an oblique asymptote. So this actually gives us 2 lessons to learn. One is that a rational function can't have more than one horizontal asymptote, and if there is a horizontal asymptote, the function will not have an oblique asymptote, and basically the oblique asymptote and the horizontal asymptote can't happen together. So with this message, we're going to wrap up the lecture for today. What we have tried to do in this lecture is we've talked about vertical asymptotes and horizontal asymptotes. We've practiced problems, but the basic objective of this particular lecture was to bring together different ideas about asymptotes from various sources and put them together in one place for you. So I hope that this lecture has helped. I've also tried to clear up various misconceptions that people have about certain ideas relating to asymptotes, and also it's important to avoid certain mistakes that students make. So I hope this lecture has been useful for you, and we'll continue from here in the next lecture, and we'll talk about oblique asymptotes, and we'll practice some more problems. Until then, bye-bye.